Just position. Or probably be over here. I'll take my food leave. High efficient. Blah blah blah. Okay.
It's just for the
So I just like this little here, right?
Yeah. I know it looks like it is. Or that's just are the slides or I guess they are. Maybe it's designated. But this looks a little different than before.
Yeah, it's a lot different. The user interface, they changed.
So it's probably showing.
It's probably recording. It's like in presenter mode, so it doesn't. It thinks you don't need to see it.
Yeah, messes up.
Oh, okay. We'll meet tomorrow.
Oh, I've got a clip on this.
That's okay. So.
That's awesome.
Okay. Just a. Oh, we're recording. We're recording. We're going wrong.
Alright,
Yeah, we're good. Even if we're not, it's it.
I'm gonna run back upstairs and grab that computer and just start doing updates down there.
Okay.
Alright, thanks. Hey guys, I think we're gonna get started.
Listen. So our first speaker for the day is Shibin. Just a little blur about him. Shibin Shin received the major in engineering from Hwa University of Science and Technology in 2012, and the MS degree in electrical engineering from the University of Illinois at Urbana-Champaign in 2014, where he's currently pursuing a PhD degree. His research is in high power density converters and photovoltaic applications.
Thank you. So if you go on that side, I'll get the video. Cool.
Good afternoon. So thanks for coming to my presentation. And today I'm going to talk about the work we kind of derived from this little box challenge project, which is like a high power density buffer in single phase converter applications. So this is just an outline of my presentation. So we'll start with a brief review of the background. So as we know, in any power conversion between DC and single phase AC, because say if the AC current and voltage are perfectly in phase, then they are going to produce twice light frequency kind of ripple. So shown here is the AC output waveform, a voltage waveform of the inverter, and the resulting power is actually a shifted sine wave about 0. So the DC power has the same average as the AC power, but at any time there's always an instantaneous mismatch between the DC and AC power, which require electrical circuit to buffer that instantaneous difference, which we refer to as power pulsation decoupling in this case. So conventionally, power pulsation decoupling is done in a passive way, in which we simply connect a very large electrolytic capacitor across the DC bus. So the energy that needs to be buffered is determined by the load. And in each cycle, this capacitor just gets charged and discharged to buffer the energy difference. And this process, this charging and discharging process, is going to create a voltage ripple on the DC side. So basically shown in this plot is the percentage ripple we allow on this DC bus versus the energy utilization ratio, which is basically how much energy potential of that capacitor is actually being used. So as we can see, as we ripple more, we can definitely utilize more and more to the full energy of that capacitor. But most applications actually put a very strict requirement on how much ripple you can have. So typically only a few percentage. So if we are only rippling a few percentage on the DC bus, then most of the energy potential of that capacitor we cannot use, which eventually result in a very large capacitor size. So the fundamental problem with the passive decoupling approach is that the function of voltage regulation and energy storage are both fulfilled by the capacitor, and they are fundamentally contradicting to each other. So what people have proposed in the literature is an active decoupling approach, which is shown here. So we connect a magnetic-based converter between the DC bus and the capacitor. So this capacitor is allowed a much larger voltage swing, so we can fully utilize its energy. Well, this converter changes its duty ratio accordingly to regulate a constant DC bus voltage. This greatly reduces this capacitor size, but the main problem is this converter has to process about 2/3 of the total energy of this entire inverter structure. So even if it has a it's highly efficient because it's processing a bulk power, it's still going to put a very large efficiency penalty on the overall system. And secondly, because this converter is directly connected to the high voltage DC bus, so it actually has very high voltage stress, which result in slow switching and very large magnetic component size. And this will typically completely offset the volume gain we have by shrinking this capacitor. And another approach to solve this problem is the stacked switch capacitor buffer, which is also called SCC for short. So it has an array of capacitors and switches. So as the load kind of goes through a line cycle, it will reconfigure, the switch will reconfigure the capacitor in different series and parallel combination to regulate this bus voltage. And because the switches only exercise a few times within a cycle, so the switching loss is actually very small. So this system has very high efficiency. But the problem is that this structure is discrete in nature, so it typically has very large bus voltage ripple because it's discrete. And it has relatively high circuit complexity, especially the gate driving circuits for all these floating switches. So both of them are not very, not the most desirable solution. So a recent, very promising solution is this series voltage compensator. So basically in this structure, again, we have this capacitor. Here we allowed a very large voltage ripple on this capacitor. Then we connect a power converter here between the capacitor and the actual inverter, and the voltage of this converter actually change accordingly complementary to this capacitor voltage. So what this inverter actually sees is actually a very small voltage ripple, despite the large voltage ripple here. So this structure has the advantage of because it's only see a fraction, it's only see the ripple voltage magnitude. So it has very low voltage stress, and it's only processing a fraction of the total power. So it's very efficient. But the problem is that the DC bus here is left unregulated. So it has, so if this DC source is a PV module or a battery, it won't work very well with this type of DC source. And another problem is, like, strictly speaking, this approach reduces the ripple here, but theoretically it does not completely eliminate this. So from this review, we can conclude that what we're looking for is a structure that, on one hand, has the capability to continuously regulate both the bus voltage and the inverter voltage, as in magnetic-based converters. And we also want to take, use this type of voltage stacking to reduce the voltage stress on the actual converter. Lastly, we want to guarantee a very tight regulation on the DC bus. So, and then next come to the circuit architecture that we actually propose, which is shown here. So in this structure, this is again the DC source with like a source resistor, and this is a typical inverter load, which is like showing in purple, which is drawing a current, a shifted sine wave current, as a typical inverter does. And the DC, ideally, in steady state, if all the buffering works well, then the DC side current is this blue line, which is constant. So in this structure, again, we have this C1 capacitor, which is allowed a very large ripple. But instead of all this per-verse solution, we actually connect this buffer converter in series with the C1 capacitor across the DC bus. And what this, so what this converter do is that we will program it to behave as a controlled current source, and it will absorb the instantaneous difference between the AC side current and the DC side current, so which is shown in red. So as long as it behaves that way, then naturally the voltage across terminal A and B will vary accordingly, complementary to C1 voltage, such that the sum of these two is a constant, which is shown here. So again, C1 is this capacitor voltage, which has a very large swing, and the voltage between terminal A and B, which we call VC3 here, change accordingly. And their sum is this bus voltage. So do note the y-axis here in different units. So the bus voltage is almost constant with a very small ripple, and this small ripple is due to like practical imperfect matching of current. So as we can see, this structure, because this this converter here only see a fraction of the bus voltage. Most of the voltage is blocked by C1 capacitor. So it actually has very low voltage stress. And analysis shows that it only processes like 7% of the total power. So the entire structure in this design example can buffer 2 kilowatts, but the actual converter is only processing like less than 140 watts at its peak power. So by doing this, we actually reduce both the voltage stress and the power processed. So this system can be highly efficient and very small. This is basically like a qualitative description of how the system works. So, and the next question is, how do we actually analyze and determine how large should we size this C1? Oh, sorry. By the way, this converter is actually implemented as a full bridge converter. So, because as you can see here, the average current through this converter is actually 0. So we do not actually need an active current source to fulfill its function. So what we do is we simply put a full bridge structure with a C2 capacitor to store certain energy and maintain the necessary voltage for the correct operation of this converter. So as you can see, C2 voltage is maintained here, so the entire structure operate correctly. So the next question is like, how do we actually calculate, how do we actually quantitatively describe the system, and how do we size C1 and C2 capacitors? So more detailed description is actually in the paper, and it's more involved than I want to explain here. But basically, the entire system, after a certain analysis, comes down to this equation. And this delta Q1 is an integration of the load current, which is fully determined by the load, and we have no control over it. And M is the conversion ratio of this converter, which we are trying to solve in this case. And C1 and C2, the actual capacitance and the initial charge on this C2 capacitor is the design parameter we want to choose to ensure this structure operates correctly. And depending on the actual circuit, it will actually impose two constraints on the actual circuit. The first one is that for this circuit to be practical, then this this conversion ratio need to have a solution. So if we solve the discriminant of this equation, then it results in the first boundary condition for sizing the capacitor. And second condition is that for a full bridge converter to operate, then basic power electronics knowledge tells us that the duty ratio has to remain between -1 and +1, which imposes the second constraint here. And basically, we can optimize for the total capacitor size given these two constraints. So the last thing to note is that this analysis is actually independent of the circuit topology we use. So here we choose a full bridge converter because it offers a certain advantage. But we can also use like a non-inverting buck boost converter or other topology. And we only need to change this constraint accordingly for different topology. And the same analysis actually apply to all these converters. So next, I'm going to talk about the control, which truly enable the application of this structure. So this control actually has been discussed in details in our compile paper. So if you're really interested, you're encouraged to refer to this paper for more details. So here I'm just going to briefly introduce the challenges and the solution we have. So for this, as we mentioned before, we want the converter current to follow a reference, which is the difference between the DC and AC side current, and which is done by using a bandpass filter to extract the AC component of the output current. And then we implement current hysteresis control. So basically, we generate a reference, and the actual inductor currents just bounce between two limits, such that the average converter current is what we want. But there are two potential problems in this control. The first thing is that in practice, we cannot program this current perfect. So like due to practical measurement errors or control offset, this current might actually have a very small DC offset in this actual value. So this small DC offset will keep charging and discharging C1 such that the voltage of this will keep drifting up, from its desired value, and the entire operation of the buffer will be disrupted. So what we do is that we add the first PI control loop to remove the DC offset from this current, and more details again is found in this paper. And the idea behind it is very similar to the common mode feedback in analog amplifier design. So And this is the first control loop. And there's like actually a bigger problem, because when this converter operates, it will, unavoidably incur certain power loss. So this C2 capacitor, because of this power loss, will gradually lose energy and it will drain to 0 voltage. Right? Then this entire converter cannot operate again. But any attempt to directly pull extra current to compensate for that power loss will result in the DC offset problem that we just talked about. So it will fight with the first compensation loop. So we have to figure out a different way to compensate this within the AC frame. So we actually come up with a scheme to utilize the remaining small ripple on the bus voltage to actually do this compensation. So again, more detail is in this paper, but just on a very high level, the power of this converter is expressed in this is expressed here. So the buffer current, because enforced by the first control loop, is a pure AC, and this VC1 voltage, because it's capacitor voltage, is again pure AC, but exactly out of phase with iBus. So the product of these two will just be a pure AC, and we cannot really use a pure AC to do compensation. And this VBus voltage, if it's ideally a constant DC voltage, then the product of AC and the DC is still AC, and we cannot use that to compensate. But practically speaking, because there's like small mismatch in practical implementation, then the bus voltage will contain a very small AC ripple. And if we time this small AC ripple just right, such that this small AC ripple is in phase with this buffer current, then two in-phase AC, the product of two in-phase AC will contain a DC component, and we can use that DC component for compensation. That's the strategy behind this. So that's the control challenge. And next, I'm going to show the long-awaited power result. So this is a photograph of our power prototype. So as you can see, most of the board space is actually occupied by passive energy storage component, especially capacitors. So in this design, we actually shrink the main energy storage capacitor C1 about 8 times smaller compared to if we use the same capacitor in a conventional DC bus, passive DC bus decoupling solution. So we will need like 1.1 millifarad capacitor in a conventional DC bus solution, but here we reduce C1 to only 130 millifarad. And indeed, C2 and the inductor add some overhead to this, but still overall the component volume is still much smaller compared to a conventional DC bus solution. So all the passive components come down to only 3.27 square cubic inch or 2 kilowatt buffer. So next I'm going to show experimental result. So to illustrate the operation of this buffer. So basically, this is the buffer running. So again, the load current, the inverter load is actually drawing a shifted sine wave here. And the buffer actually operates as expected to just draw the difference. So because they actually match each other, so the input current is actually almost a constant current in this case, which is exactly what we want. So just to look into the details of the operation of this converter. So again, the load current is shown here to use as a reference. And basically, you can see that VC3 voltage, basically the voltage here, is actually experiencing a very large ripple, which also suggests that VC1 has the same, but opposite ripple of VC1. So VC1 has a really large ripple, so its energy potential is being very well utilized. But at the same time, the bus voltage is maintained almost constant because these two add up to a constant. And C2 voltage, because of the compensation loop I just introduced, maintain a well-regulated value here. So here is just a zoom in. So basically, this bus voltage here is DC coupled, so it shows 400 volt. So next we take a really zoom in look at the AC component of this bus voltage. So as you can see here, we have almost like 150 volt peak-to-peak voltage ripple on this capacitor, but what appears on the bus is less than 4 volt peak-to-peak ripple, which suggests this method to be very effective. So this is just another experiment without showing the entire system under a transient condition. So you see the load current actually jump from 50% of the load to 100% of the load. So all the signals change accordingly, but after a short transient, they all return to another steady state, which suggests the control is stable and robust. So this plot shows the efficiency as a function of the average output current, or in other words, the load level. So this converter is designed for 450 watt input source. So as you can see, at the rated voltage, it's actually very efficient, about 99.5 across all load run, all the way to full 2 kilowatt. And as we go down in voltage, because it's processing less and less power, the efficiency is lower, but still, for all these conditions, it's all higher than like 97.8, which is highly efficient compared to other works, relative works. And again, with this 2 kilowatt we measured, and the component value we actually measured, so this entire board actually achieved 611 watt per cubic inch, which is like already record breaking, I think. So to summarize, so what we have achieved is a series connected buffer architecture that achieve very low voltage stress and small bus ripple with a relatively simple circuit. And this, as we have shown experimentally, it has very high efficiency, about 97.8, and very high power density at 611 watt per cubic inch by component value. And we also briefly introduced the control scheme that enable the entire structure to operate. And there are two kind of like fundamental ideas behind this design that like enable this entire idea to work. So the first one is we use a capacitor to block high voltage. Instead of using switch to block high voltage, we actually use capacitor to block high voltage. So this is the same idea used by many multi-level converters. And the second idea is that we control the full power by processing only a fraction of it. So this is the same idea behind differential power processing. So that's the end of my presentation, and we also want to acknowledge all the sponsors. Thank you, everyone.
Did anybody have a question?
Page 19. How do you define this efficiency?
Well, it's just like the we have two power meter, one at AC side, one at DC side, and just to ensure it's free of any like kind of interference with ripple, we use this two meter to measure 1 second continuously, integrate the number for 1 second continuously, and we use the ratio. So that's the power, integrated power on the AC side over the integrated power on the DC side for 1 second.
This is efficiency of what?
Well, yeah. So for this structure, basically you can look at this. So we'll basically connect like this is the entire buffer system. So we take a measurement at the power here coming out of the DC source. We take a measurement on the power here going into the inverter. So that is how we do. That's a very good question. I will make sure.
And the just mentioned the voltage level. What is the power level?
Power level is just a product of these two. So you see, this is say 5 amp.
Oh.
Sideline 450 volt. Well, because we have a 10 ohm resistor source, so that minus 50 volts, so that's 400 multiplied by 5.
Can you just convert a non-unity power factor?
I think so. We haven't experimented that thoroughly, but I don't see any difficulty. But that's definitely what we're going to do next. Thanks.
The inverter works at non-unity power factor.
Yeah, as your controls. Okay, thank you very much.
I guess while they're getting ready, our next speaker is Enver. Enver Candan. Received the dual BS degrees in control engineering and in electrical engineering from Istanbul Technical University in Istanbul, Turkey, both in 2012, and the MS degree in electrical engineering from the University of Illinois at Urbana-Champaign in 2014, where he's currently working towards his PhD degree. His research interests include data center power delivery systems and isolated DC-DC converters.
Thank you. Oh, thank you. Yes. Great. Thank you. Hello, everyone. Thanks for coming to my presentation. I'm presenting this in a conference in a week, so I appreciate your questions if there is any part that's not clear. So the title of my talk is a series stack power delivery architecture with hot swapping for high efficiency data centers. This is a brief outline of my talk. I will first introduce a conventional data center power delivery architecture and talk about its limited efficiency limitation. And then I will introduce this our proposed architecture, which is we call it series stacked power delivery system. And I will briefly explain how it overcomes the efficiency limitation of any conventional system. And of course, since we propose a new power delivery system, there will be some challenges for the practical implementation. I will going to address these challenges with our custom design experimental test bed, where we use these computers 12 volt, with 12 volt motherboard input and a real life test scenario that is common to many data center. And then I will conclude my presentation. So Blue Waters that we have in campus, it's a data center, it's a supercomputer. It employs many servers. So this is a picture of one of the server blades that they have it in the data center. That's a state-of-the-art data center that employs very high efficiency power converters throughout the power system. So since these servers are computers, basically they require a low voltage DC voltage. So in order to power them, we need some power converters to connect to the grid. And in a data center, since we have so many servers, we have so many of these DC-DC converters. So in this architecture, this is called DC power distribution, and this is the one that is used in the blue waters. What they do is they bring the grid, the AC power to a server rack, and then each server rack has its own DC, AC to DC converter in order to regulate a high voltage DC bus for the server rack that includes many server blades. And then each server has its own DC to DC converter. That's the one that you can see here in this picture. That steps down this high voltage DC bus to a server, to a lower voltage for the server. This architecture is mainly preferred in many data centers. However, it has an efficiency limitation. So since you might guess that every data center is working 24/7, sorry. Yeah, 7/24 is the one that's used. Anyway, so these DC-DC converters are processing the full server power throughout the operation of the data center. And since you are building these DC-DC converters with practical elements, the efficiency of this DC-DC converter is somewhat limited. And since it is processing the full server power, when you think about the number of the servers that you have in data center, the overall system efficiency is in fact limited by this DC-DC converters. So here, if you look at this, for example, this DC power distribution architecture is a derivation of a power converter that is originally designed for a single converter. Okay, this AC/DC stage maybe came out of the server rack. However, this is basically what we have in our computers' power supplies. So the question that we are trying to answer that, okay, this is 2015, we have so many servers in data centers, but why do we still use a power architecture that is originally designed or originally taught for a single computer? So having this as a starting point, we propose this series stack architecture for a number of servers. So what we do is we connect these servers in series. So their input voltage is used to build up this high DC bus voltage that is regulated by the AC to DC conversion stage. So this eliminates the step down, the DC-DC power conversion stage, and then also provides this inherent step down. And here, once we connect these servers in series, the bulk power that is consumed by these servers, the average power, is connected through the series connection, and the current is always reused between the servers, which tells us that we eliminate the DC-DC stage, so we do not process this bulk power that the servers are consuming. However, when you connect loads in series, if they tend to consume different amount of power, their input voltage is going to vary. And this is a dangerous situation for our servers, which is an expensive hardware. They have very strict input voltage range. In order to satisfy this voltage range, we employ these differential converters, as they are shown as DPP here. They provide the difference current between the bus current and the server current in order to regulate the series connected server voltages. And the key advantage of this architecture is that instead of processing the full power as in the conventional architecture, we are only processing the mismatch power, the differential power, the difference power between the servers. So if we can somewhat manage the servers to consume similar powers, the amount of power that we process in this architecture is going to be greatly reduced, so which is going to result in a tremendous increase in system level efficiency. So this idea is called differential power processing, series stacking and differential power processing. There are many ways to do that. The way that we prefer to do it in my research is called server to virtual bus. The virtual bus is a capacitor bank that is connected in parallel with all these differential converters. This enables us that if any of the server has a, let's say, extra current that is consuming, that has extra current than the bus, so that its voltage tends to vary, we can shuffle that, we can store that extra current in this capacitor for a temporary time until another server needs current in order so that its voltage needs to be regulated. And since all these DC-DC converters have access to this virtual bus, we can basically shuffle all these extra currents between the servers in order to regulate all the series stack server voltages. We have So since we are introducing a new element in the system here, which is this virtual bus capacitor, we are free to choose its voltage rating, and if we choose it as the same as the server voltage, here we end up not doing voltage conversion again. We can rate the DC-DC converters to 1-to-1, and we can make the converters very efficient. We can use low voltage switches to make them quite small. And this is basically the advantage of this architecture. And we have presented the conference paper and also published how this architecture actually works, or some implementation details in this paper. So I refer the interested audience to this paper. So advantages sounds really good, but of course when we propose a new architecture, we will end up having some challenges. So the first thing that might come to your mind is that, okay, you are connecting all these servers in series, and then each of these are going to stay at a different voltage level. And how are you going to communicate between these voltages that each of these stay at a different voltage level? So the Ethernet infrastructure that we have nowadays, it provides 1.5 kilovolt isolation. So this is in fact not a problem. However, the new trend also in the data centers is shifting all this communication to fiber optic infrastructure, which by definition doesn't really have any electrical connection for the communication. So the communication, in fact, is not a challenge. The voltage regulation as a power delivery standoff point, the series stack voltage regulations and the voltage regulation of this virtual bus is a problem when we have non-even power consumption between these servers, and we developed an intelligent power voltage regulation algorithm where we don't communicate between these DC-DC servers, DC-DC converters, and we are able to regulate both series stack voltage, series stack server voltages, and the virtual bus voltage. And we presented last summer. We presented this algorithm in last summer. I'm not going to get into the details. Another challenge that we have in the system is hot swapping. So what is hot swapping? So the servers are computers, as I said, so quite often require maintenance. So what happens in the conventional DC, what happens in the data centers that use conventional DC power delivery architecture, the operator comes and then just like pulls the server from the rack. And since every server has its own power supply, this doesn't have an effect. This doesn't have an effect on the system. However, here, if you try to pull one server out, I think it is very clear to everyone that we are going to lose every server in the series stack because the servers are actually forming the main current flow path. So we need that in the series stack so that all the servers, we can deliver power to all the servers. So this is the hot swapping challenge that we have. So I'm trying to address this experimentally. Let me show you the challenges, the implementation challenges in this hot swapping problem. So one thing that we want to make sure that, let's say that this server 2 is swapped out from the series stack, we want to make sure that all the remaining servers are continuing their operations. And in order to make sure that in order to guarantee that we should make sure that all the remaining server voltages and the virtual bus voltage is still being regulated, even though there isn't any server here. And how this is done is that let's say that again server 2 is swapped out, the differential converter for the server 2 is should be able to handle this bus current. We are going to inject this. We can inject this bus current to the virtual bus, and then all these other differential converters are going to revise the excessive voltage in the virtual bus, and instead of using the full bus current, they are just going to reuse the current that is stored in the virtual bus. And another thing, when you think about the practical application, since each of these servers are staying at a different voltage level, let's say that the server 2 is swapped out. These two leads that make server to connect the series stack, they are at a higher, they are at a higher voltage. So an operator may touch to these leads and may be electrocuted. So we have to make sure that when a server is isolated when a server is swapped out from the series stack, it should be those leads should be completely isolated. And also these servers, I don't know, have you ever see a server power supply? They normally have very high input capacitor in order to provide a ripple-free DC bus for the server itself. So once a server is plugged in, there is a phenomenon called inrush current. So this capacitor at the server input tends to pull spiky current, and since in this series stacked architecture, this spiky current is difficult to be handled by these DC-DC converters because it happens so instantly. It is gonna tend to flow through this bus current, and this is going to mess up all the voltage regulation that you have in other servers. So this is called the current limiting. So in order to address these challenges, we have built this interface circuit that stays between the series stack connection and the server, which is basically three switches. So we have both high side and low side switches to provide complete isolation. And also during the swap in moment, in order to limit the inrush current, we are having a current limiting resistor here. So when we first connect the server to the series stack, we are only using this M2 and M3, and the input current to the capacitor is delivered through this current limiting resistor, which prevents the current to have a spiky nature. So this is the differential converter that we use dual active bridge DC-DC topology. It is very simple. We use simple phase shift modulation, and it's since we don't convert the voltage, we are using the same switches both at the primary and the secondary input, the secondary side of the transformer, which gives us a very nice symmetric design. So that like depending on the power direction, there is no efficiency difference. So the circuit looks identical from both inputs. So this is our experimental setup. We have Dell Optiplex Core2Duo computers that are configured as servers. We have interface circuits that stay between the server and the series stack, and so does the differential converter. So we built a 4-server testbed. We have 4 of each of these. What we use to show you the voltage regulation and the server currents is the data acquisition unit. We are sampling all the annotated signals here and calculate input power. That is the input power is the input power to the series stack, which is the V bus times I bus, and the output power is basically the power that are consumed by each individual server. And I also sampled the virtual bus voltage to show you that virtual bus is being regulated as well. And as a real-life test scenario, I am using a stress command in the Linux, which is a workload generator that's basically calculating a number. So first, I would like to show you how we swap a server in and how it initializes. So in the beginning, all these servers are isolated from the series stack, so all these switches are open. So once we apply this bus voltage, these DC-DC converters are basically shuffling they are basically making sure that each of these capacitors are regulated to 12 volt. As you can see here on the black, this is the V stack. This is the voltage labeled as V stack 2, which is the voltage at here. And around the 10th second, we are turning on this. We are closing these switches. So we have a less than an amp constant current to charge the input capacitor of the server, and you can see a linear increase in the server voltage. And then after half a second, we are turning on the M1 and turning off M2 in order to make this power flow path highly efficient. And then, like after a few seconds, the server realizes that it has enough voltage, so it initializes itself. This is the server currents for an example test scenario, which uses the computation test that I mentioned a few slides ago. So this entire test takes 6 minutes. The first 2 minutes is basically the server initialization here. And then after all, we make sure that all servers are initialized. We run this stress command in the servers for a minute. And if you can see here around the second 190, the server 2 current drops to 0. So here what we do is we basically open these switches instantly without letting know the control algorithm that we are going to hustle up the circuit. So this is basically an extreme scenario that you would come across in a data center. And then for 1 minute, approximately 1 minute, the server 2 is unplugged from the stack. And as you can see, the other servers are still consuming power. So the power delivered to the bus current still flows through the remaining servers, and so does the DC-DC converter of the server 2 shuffles it through the virtual bus current. These are the server voltages. Here you can see that even though the server 2 is swapped out between second 190 and 250, the server voltages are still being regulated to 12 volt. And here actually what happens is that the DC-DC converter of the server 2 is regulating, it still keeps regulating this the voltage labeled as V stack 2 to 12 volt.
Being hot swap, just give us a second.
Yeah. So these are again zoomed in version for the swap out and swap in instance. As you can see here around the second 190, we swap out the server 2, and black is again here the voltage labeled as V stack 2. It is being regulated to 12 volt, whereas the voltage, the server 2 voltage slowly decays from 12 volt to 0. And you can see the current here as well. The current goes to 0 immediately. And after approximately 1 minute, we slowly turn on we still, as by using the procedures that I described in this in a few slides ago, we close these switches in a manner so that the voltage increase in the server 2 is linear, and the current that causes this voltage increase is constant for a few milliseconds. And then after that, the server initializes again after a certain amount of time. So in the beginning of my talk, I talk about the system level efficiency, and we did all this complicated structure to have higher efficiency. So let's look at the system level efficiency for 4 server rack for 6 minutes. So here I divided up the efficiency numbers for each section during the test. So for example, during the server stack up, which takes like approximately 2 minutes, we have 98% efficiency. And once the server test has started, we are having around the 98% efficiency, and we only see the low or conventional efficiency numbers around the hot swapping part, where we are processing more power. So we are processing more power than we should be. So that's why the efficiency is lower here. And after the server 2 is kicked in and initializes, the efficiency numbers goes up again, and the overall efficiency for 6 minutes is around 97.73. Is 97.73. However, here I would like to take your attention to that the hot swapping part, especially which causes this lower efficiency, is almost 1/6 of the entire test, which is in data centers, in nowadays data centers, the hot swapping time. If you realize a server failure, you immediately change that and you immediately replace that server. And when you think about you run the servers for 24 full hours, your time that you spend in hot swapping operation is not 1/6 of your time. So this number is actually, when you apply this to a real server, this is going to approach to this 98% limit. So to conclude my presentation, we apply again the series stacking and differential power processing on real servers, and we presented hot swapping operation for the first time in a series stack architecture. And the system level, high BHE, high system level efficiencies as like 98.39 peak and 97.73 overall. With that being said, I would like to acknowledge our sponsors, Texas Instruments and Google, for funding this work, and there are investors like that. Answer those as well. Yeah.
How much more efficient is this now?
Yes, so that's a really good question. Thank you. I am not able to compare this architecture with. So actually, we built this. So actually, we built this DC power distribution with this exact same DC-DC converter in the lab as well. However, I didn't really have time to compare the hot swap part operation. However, for the one that we didn't demonstrate the hot swapping, we just demonstrated the steady state operation where we are not hot swapping anything. We are only using this series stack server at a balance load. At that time, we are able to reduce the average power loss in comparison to this DC power architecture by 40 times. So when you think about it, okay, these DC-DC converters can be highly efficient, 96% maybe, but going from 96% to 98% means that you have to reduce the losses by half, and it is a little bit difficult when you with the circuit level improvements. However, since we are proposing here a system level architecture that is aimed for multiple converters, multiple servers, we are able to report that the average power reduction.
How do you determine the hotspot position and turn on the, I guess?
So here, I just waited one minute until to plug in the other server. However, this control algorithm that I have that regulates these voltages, I could have kept this for 5 minutes too. The control algorithm that regulates these server voltages doesn't require any input from the user. That oh, okay, I'm hot swapping now or I'm swapping back in.
How is that?
So okay, so I placed in a real life application. You can place the server back, and then there can be a button for a user to send the command to close these switches. Is that clear? And it depends on the user. So once you plug in the server back, you can say that the server is connected. So you can close these switches, and after that point, the server is going to initialize, and then it is going to continue its operation.
So your question? Were you going more for the actual circuit for the hot swapping?
Yeah.
I think So I think he was going more for the. If you go actually to your pre-charge circuit.
Okay.
I think you were asking more. How do you physically turn these switches on or not?
No. First, how do you select the resistor value?
It is experimental. We just, we made some calculations. This is basically once the server is not working, it only shows a capacitor here. So this is an RC filter. So you are basically charging a capacitor through a resistor from a 12-volt source. So we started from that, but of course the input capacity depends on your server. So we iterated every time, so that we.
Have you considered the SOA of the amplitude switch?
What? S?
SOA.
SOA of the?
The switch to series.
Which one?
Amplitude.
M2? Yeah, this is rated for the full bus voltage.
No, for the inner current.
For the inrush current.
Can you handle the inner current for like certain?
But the thing is that here, the inrush current, inrush current is 800 milliamp. Of course, this is rated for, I don't exactly remember the rating of the switch, but yes, this is, that's a power MOSFET, so it can handle 800 milliamp.
I hope so. It's a power.
Yeah, it's a power.
So in the conventional topology, the servers are running on the same ground, right?
Yes, correct.
So but this is running on different voltage levels. Does the server require to run on the same voltage?
For communication purposes,
Yeah.
they do not. So there are different structures that can communicate with different voltage, the service can, at different voltage levels can communicate between each other.
Now, the one change you have to make, right, is that in a normal server today, your negative terminal is tied to ground, which is the chassis. Right? So now, of course, the chassis here that this one sits in should not be tied to the negative terminal of the server. So the server, the motherboard itself has to sit floating inside some, the metal structure that's in, right? So that's not that hard to do because inside the power supply, inside your server, there's a lot of isolated nodes anyways. But that's a design change. You can no longer tie the negative terminal of the server. It cannot be ground tied anymore.
When you have more than one server swapped, how are you able to handle that? And then how does that affect the ratings that you need for your DC-DC converters in and out of your virtual bus?
Here, that's a good question. Thank you. So these DC-DC converters are rated for the full bus current.
Okay.
I didn't experiment with it, right? If more than one server is hot swapped. And what I can say that is that so we have an efficiency drop when like even one server is hot swapped. So this is 96%. Okay. So depending on how many servers you connected in series, there might be there is probably a sweet spot that if more than n server needs to be hot swapped, it is better you turn off the system in order to keep the high efficiency. Yeah. So I haven't experimented with it, right, but this I didn't pick this server 2 intentionally before. You can swap out any server.
Yeah. And your hardware is safe.
Yeah, and hardware is safe. Yeah. You had another question, I think.
Well, it was built in. Compounded.
Chris, you have a question?
Well, Alex took the words out of my mouth.
Oh.
But in theory, these voltage stack domains can come up to their rated voltages without the servers attached.
Yes. Yeah. That's how we initialize the circuit. So first the series step. First the servers are not connected, and these DC-DC converters are basically balancing the charge between these capacitors so that everything is around 12 volt. And once we make sure that this is kind of a power good signal for us, then we turn off all these switches instantly. That gives, since all these converters are also identical, that gives almost identical initialization to all the servers at the same time.
Can the virtual bus get full?
Yes. I mean, it's a practical component, of course. But if you note that, I mean, if you think about this in the data center, there are if these 4 servers are staying in one rack, there will be another 4 servers that are staying in another rack next to it, and there will be another virtual bus. So, like UPS swapping, you can. I mean, if there's a failure in your virtual bus, you can maybe you might be able to connect the rack next to you and use its virtual bus for temporary amount of time.
But so if you're saying that the virtual bus can get full, what happens if it gets full?
Yeah, you need to isolate this, of course, and then what do you?
I guess the question is more with respect to your control implementation, right? Your controller here ensures that for DB to get full, that means that the voltage is at the rated voltage, right? If it goes above that, then it explodes. That's what full means. But I guess what wasn't shown in this talk is your control algorithm to ensure that the V bus better never go more than above full.
So of course, maybe I just fast forward. I fast forward. Yeah, the control algorithm makes sure that this doesn't go above its rated voltage. Okay. If that's, of course, this is a practical element, and there is aging and everything. So you need to do maintenance for your virtual bus as well. But it is very. It's not highly expected that the virtual bus is going to explode while you are regulating this voltage.
Good.
How many servers can you stack before you start running into needing more insulation inside the server?
So yeah, that's a good question, and that depends on your service basically. However, like architecture-wise, there is, I mean, each of these DC-DC converters are identical. So this works with 4 servers, 6 servers, 8 servers. The power architecture-wise, we do not have any limitation. Unless you hit you connect maybe 30 servers in series and you hit your DC bus voltage limit. Of course, you cannot stake more server than you have. is this IDC bus voltage.
And that's about 400 volts in a data center.
Yes, there's about 400 volts.
It's about 30. So
Yeah, just 32 servers if they are 12 volts.
So Enver will get his rubber gloves out and deal with 400 volt supplies shortly.
Thank you.
So this wasn't cooperating very well.
It's okay. It's fine. Thanks a lot.